Yes, hi guys. Sorry, couldn't find my mic. Yeah, today we're gonna do one more example, a much more complex one. It's inspired by everyone's desire to do something related to NFT. Um, so if you have received the PDF for it, it should be in the README channel. Let me open it myself and I'll cast the screen in a second. Let me actually close my camera. Cool. Okay, so let's. All right. Okay. Anyways, so this is kind of the layout of how the thing's going to look today. But yeah, so the services. So it will enable people to bet, gamble, an arbitrary amount of money. There's going to be no edge, so it will be akin to betting black or red in a casino, but there's no edge to the house. It's going to be 50-50. The division is, well, the choice is to the random, as it's hard to get VRF yet, but we've added another functionality to it relating to the NFT, which will mean that only people that have NFT of a certain collection will be allowed to do that gamble. If you don't, you will lose all your money. You will lose all your soul. So yes, it's one of those where it's good to read the contract or any kind of statements provided by the front end, whoever's hosting it. So this is the diagram for it. So the coin flip program is the other one. It will own just a bank account, and in it we're gonna have a set the banker, who is the person that has got authority, and the person is going to set which NFT mint is the one that will be acceptable. The program will read state of other accounts, and two of them, those accounts themselves will be owned by SPL program, and they are token PDA, and that's referenced or derived from the mint PDA. Those will be used to gauge whether someone has got the right to do something. Program will have only two. There will be more added for the homework, but the actual functions, there's only init bank, which will initialize the account. The account is not a PDA, and as I say, it's the permitted public key of the mint and authority of the person who can manage it. And there'll be a function called gamble, which anyone can invoke it. And if the call does not have enough LAN ports to the gamble, the specified amount, or the bank does not have enough to return double the amount, the transaction is reverted. However, if the caller does not own the correct NFT, they lose all their SOL. And if they own the correct NFT, they are allowed to gamble. So that's sort of the layout. Let me pull again. Okay, so something did pull. Okay, SPL. So let me close everything here. Okay, program SRC. Okay, so this is the program, as I said. So let's start off with the accounts. This time there is only a single account, which is the bank account. It has same permission, authority, permitted mint, and this is for later. And this is the context relating to it. So there's no seeds in it, so we know that this is an PDA. This is just a normal account. This happens just once upon invocation, can be reused many times by other people. And what the person starting it, who the banker is, will provide is an account that they've derived, they got the private key for, and it's signed for from the client. And this is this account which is going to assert those few things. So let's see the function. It's the much smaller one. So as well, it's got two arguments. So this variable tells how much money the person wants to deposit. So if you want people to gamble or do any sort of activity, we as the house, like in a casino, have to have funds for them to be able to do it. So program will reject transaction if there is not enough money to allow person to get double of what they staked. So we allow person to deposit some amount. There's no minimum amount, it's just whatever they choose to, but if it's too little, it might not work or it might discourage people from playing. As it is exactly 50-50, long term it should average for the balance to neither grow nor shrink, but of course in a short space of time it might and it could go down or up quite a bit. And the other thing is the permitted mint, which is the public key of the NFT mint that all the owners of it will be able to call it. So as before, we instantiate, say, a local instance of a bank account, and we set the authority of it to be the caller, and we set the permitted mint to be the one we've passed over. Then we deposit the money, which we're invoking the system program. We're creating a transaction, and then we're invoking the system program. So we're sending lamports from the caller, the banker. We're depositing it to the account we have provided, and the amount we're sending is the one that that person has specified in one of the arguments. And here are the accounts necessary for that CPI call to the system program. Okay, so that's this one. Let's see the context for the gamble part. So gamble. So we're gonna use the gamble amount from within the context for doing checks. So this checks and this check. That's why we've added a macro which specifies that this is going to be used. The accounts that are being passed right now is the system program, bank, caller, which is, or gambler would be, I suppose, more accurate, account of the mint, and the token account of that specific token. Let's see that the function. So it's the gamble function. Here, just yes, the logging of the past account. So basically, what happens is all of these are related in a way. Oh, not in a way, they are related. So the token is derived from the mint, and the mint is specified in a bank. So if all of these are exactly the same and the ownership is correct as well, that's how we'll know that someone is permitted to do stuff, to proceed with the gambling. Just like before, we instantiate structs that we can access for the purpose of this function. Now, there is this thing you know about the associated token address, which is basically a way to look up whether someone has a specific balance. So anyone could provide any accounts, and we only want to allow people that have the right permission to do it. So what we're going to do is we're going to rederive this address using the SPL functionality for deriving the associated token address, and for that we're going to use the caller's key, and we're going to use the address of the mint. So this is this variable, and here we're going to run the checks to ensure that the caller is actually allowed to do it. So the first check we do is that at the field of mint of the token account, we're checking that is the same as the one of the permitted mint. So provided tokens mint. We're going to check again. So basically all these three things have to be the same, like the one stated here. It could have been done in a single statement, but it's a little bit more clear this way. We check that the mint field again of the token is the same as of the mint account that has been provided. We check that the amount stored at that token account is more than 0. And we check that the address that we have rederived locally is the same as the one stored at the key of that token. If you pass all these tests, it means you're an owner of one of those exclusive NFTs. And we come to the part where we do the coin flipping. So, as we've said a few times, it's a little bit awkward getting at the moment true source of randomness. You can't do it for commit and reveal. You could look up exchanges and kind of work indirectly to get it. So this is pseudo random, but how we went about it is to get the clock timestamp. And I'm sure, there is, as you guys have heard, the clock isn't very accurate now, but that's maybe for the better for our example, because nobody knows what it is. Should this be actually live and your friend was actually running RPC node, and he could ensure that your transaction gets submitted at a certain time, you could actually cheat the owner of the bank. But without that, it does serve this purpose of showing it. So what we do is we get the clock, and we pretty much mask it. As in mask it, we do an addition over this massive U64 field. And what we get in the end is just a number at the end, which can be 0 or 1. So here it happens. So if it's 1, send money from the loser to the winner, which is the bank account. And if it's 0, we do the opposite. We send double the amount of money from the bank account to the caller. So there's a bit of logging. Well, so we do this is those are, the compiler is going to know eventually what these are, but at the moment they're unknown, and we basically set them based on whether on the match statement, whether it's 1 or whether it's anything else. It's easier filling it like that. If it's 0, it would ask us to do another one, but it can only be 0 if it was to be masked like this. So in this case, it is actually the person transferring it to the program managed account, and as such, this syntax where you conduct the transaction and submit it to the system program has to be done. But again, as we've seen before, is if it is a program that's managed by you as a program, it's any of the accounts that you own and the lamp ports under it, you can use this much easier syntax of subtracting and depositing lamp ports. So it's a little bit more succinct. There's logging going on. And so this is the happy case in a way that you have 50-50 chance of losing money, but only the money which you've provided as the gamble amount. And if you're lucky, you get double that amount back. So it is just a little bit of a fairer roulette wheel. But this is the second case, which is your account gets drained. So if you can read the instructions, if you can see what the contract does, because of course it will be open source code, then you'll know that if you do not have the right NFT, then you're going to lose your money. So this is the second case, second option that can be made by people that call it. So yeah, you signed a transaction, you're happy with the outcome of it, and just like the initial case, whenever we're transferring on the behalf of the caller to the account managed by the bank, we're doing exactly the same here, except this time the amount that is being transferred is all of the lamp ports that the person has. So that's the difference, and that's the two functions for it. So we'll go into test for it, and I'll show you how we can ensure that we achieve the functionality that we set out to do without, for example, not taking money from someone who doesn't have the NFT, or the opposite, taking all the lampers from someone who is part of our exclusive fun club. So let's see where we are. So let's go example.
Examples, I think I renamed it. Yeah, to plural examples.
Okay. Oh.
Examples. Yeah. Sorry.
Okay, sorry, no worry. Okay, yes, I should have spotted it. So yes. So as before, we're gonna anchor build. So I'm connected to the local net. DevNet has been very, very slow. I timed it. It took me 3 minutes to deploy a contract. Sometimes they didn't deploy at all. It's not very conducive to working efficiently. Whenever you run an instance of your local validator, that includes already SPL program library. So all of the token functions like token lend, swap, and so on, they're actually available to you. You don't need to redeploy it. I don't think that's the case for Metaplex. So the decorators for the SPL, I believe, should you want to use it, you'd have to redeploy that contract and use it, but SPL comes right away with it. As this is going to get done, because it was a fresh pull, that means my target was empty. I'm going to get new keys. I'm going to have to replace this and redeploy it. actually have to run npmi as well. Okay, well, I guess, well, okay, it's okay. I suppose I can maybe start chatting about the test then. So yeah, as you see, it's quite long. I did write some helpers to make it a bit shorter, but it could be a few more. The red lines are showing because the IDL has not been generated yet, so there's nothing really for it to look up. Once this is done, that red squiggly line should disappear, and npm libraries are installed as well, so shouldn't get any errors about missing them. And yeah, we're going to be testing NFTs, and we're going to have accounts which have NFTs or are to have NFTs, and they don't at the moment. So there is a library for it, which is Solana SPL token, and these are the functions we're going to be using. So, unlike Sol balance transfers, it's a little more inconvenient. You have to create token accounts. You have to create associated token accounts. For the actual program itself does not need associated token account as it gets derived again. It's needed here in order to check that, for example, an account has or doesn't have a given NFT. So it's just, this was a normal setup. We're getting the program handle from imported IDL. We're creating the keeper, which is going to be the bank. We're setting an amount which is going to be gambled. I think this is used. Lampers per sol. That's basically, that these lampers is just one sol. Those are going to be all the wallets that are going to be used. So it's the banker. It's the address that's going to own one NFT. There's going to be an address that's going to own two NFTs, just in case for some reason it would reject anyone that has more than one of the same collection. And there's going to be an address that at the beginning is going to have no NFTs. And this is the mint authority. This is the account that controls the mint and is capable of minting new tokens. So why do we have two collections? Well, because it's good to check that the functionality works just as well for, that it only works for our NFT collection rather than, someone with an arbitrary NFT collection being able to do it. So we'll have to have a keeper, a mint account, as well as token accounts and associated token accounts for each of the accounts. So actually, these are, I think, the same ones. And then the same thing for the collection two. Collection two is just one test. So let me actually deploy this and substitute the keys. Okay, so we have one in a program file and then the other one in anchor.toml. Okay, and then recompile it with the new key of it. Okay, and then anchor run test to execute all the tests in a test folder, which is just this one. Okay, so actually, I have a mistake. Okay, so the declared program. Okay, so what's wrong with this? So okay, so apparently there's a program mismatch.
You change the declare ID macro in.
I did, yeah, but and it's saved as well. Okay, so let's learn Anchor build. I mean, it's already did build, but
Deploy again, maybe.
the wrong number. Mm. Then this, okay, it's localnet. I'm localnet as well. Yes. Okay, I'm gonna get the deploy. Oh, wait. Okay, the name's the same. Name's the same. Okay. Okay, so yes, stressful as always, but it did actually work and all the tests passed. So let's see the test in more detail. Okay, so yeah, after we, so these are just holders for accounts and public keys that are to be created. They don't exist yet, one for each collection. Here are a few functions which I've added that kind of simplify things. They get reused quite often, the top-ups, and I don't know, I just rather have a function to call with an array of accounts that need to have money deposited into them than do it one by one. You will often get an error about I think it's 0x01, which means yeah, the person does not, that the account does not have money. It's not very clear, but that's why it's good to top up all the accounts. Um, and yes, this function will yield you a balance. So these functions are kind of stateful, as in they use a local variable. This one, which has been defined earlier, they're not in a different file. They're not stateless. But what we do is we pass it the associated token address and its address, and this function, which is from the SPL library, it returns to us that account, and we get the amount on it, and we cast it as a number because it's a big int, and it gets returned. So this is just a little helper. And this function is a helper for, actually, I'm not sure that's used as well. But so this is the before, this is the setup for the test. So the first thing is we top up all of the accounts, and then we do the amend for the collection one. So this has been defined before. So it's this is going to be the public key of the meant key. So what we're fitting to it is the authority of it. So actually, let's see what it's telling us. So yes, the connection, payer, mint and freeze authority, which is the same for us. Decimals is set to 0 because it is an NFT, and the mint keeper, and the other stuff is left as is. Actually, that can be left undefined too. I don't think it has to be filled in, but it is. And then the program, which is the, I don't know, I guess people could have their own spin-offs which have some, for example, the Metaplex functionality. You could do that by just forking the program and adding stuff to it rather than indirectly working with it for PDAs. Then we create 3 token accounts, one that's for each of the accounts. So there's the guy that's going to own 1 NFT, one's going to own 2 NFTs, and one that's not going to have any NFTs. 3 accounts for them. And then we create associated token accounts as well. And again, they're going to be for each of those people. And this is the additional one. So in one of the checks, just to be sure that you can't actually invoke the functionality without having it. So we are creating an associated token address for an account that will have an NFT value of a different collection, but this associated token account is from the collection number 1. So this, if you were to call it and check the balance of it, it will show you 0. So that was just a setup. And here we actually mint the NFTs. So what happens here is, so we're invoking it as a ment authority, providing the ment PDA, and we're saying who will receive that NFT, which is member 1 ATA. And what's the last field? So one, destination, amount, authority. Yes, so passing the keeper, we're saying that it is the actually authority calling it. This is the payer, so that could have been actually anything. Yep. The second person, so the member to ATA, so that's the ATA of the NFT owner that would have 2 NFTs. So just for the sake of testing, he's going to receive 2 NFTs, and the third one doesn't have any for now. And here we're minting another NFT collection to the account called different collection owner. So it's the same steps. So we're creating the mint account. We're creating account for the token, and we're creating a associate token address for that user that will hold the NFT from a different collection. And we're minting him or them a single NFT. So that is the setup. So yeah, you have to do that. Well, I mean, that has to be executed. Depending on your test, you could change from before to before each. Okay, that's quite a long one. But yeah, so that could be before each, depending on how you choose to do it. Okay, yeah, so that there could be more sanity tests on it. So initializing the bank account. So actually, let's split that by the side. So this is the context that we're calling behind this. Okay, so these accounts are, these ones are easily accessible. They're defined up above, and they're not quite global variables, but they can be accessed here. So as before, we're accessing the method called initialize bank, and we're passing it the big number of just a random number that is going to be the gamble amount times 24. So yes, there's enough money for quite a lot of attempts, and we're passing it the key of an account that will restrict the functionality to the people that own the NFT from that mint. So basically, we're matching exactly what is here with the accounts. So there's bank, which is the bank's public key, the banker, or the color of it, which we're passing, system program ID needed. What are the signers here? Well, this account is not a PDA, so when we created it earlier, we have to sign it that we know how to derive the public key of that address. We have the private key for it. That's why we're signing it. System program is going to be happy, and they'll create that account. And the owner, the one with the ability to modify it, will be our coin flip program. So this is the first test. It's test. Yes, it initializes it, but yes, there could be some sanity checks added, which would check that fields have been set correctly. Okay, both gambling outcomes are fulfilled. So what's this one about? So if it is truly to be a coin flipper or a roulette like, it has to accomplish both of them. So there are Boolean, which mean that either of the outcomes have happened. So upon bank losing or the gambler winning, we said gambler won, and upon the opposite happening, we said gambler has lost, and we basically mark them. So it will run for 20 times, and the odds are pretty good within that amount of time. At least one of each will happen, and in our case, it did. I used to have a login here showing it happening, so it can happen any amount of time, and it is possible that it wouldn't happen at all. It's similar to deriving PDAs. Really, when you derive a PDA, you have a 50-50 chance of it succeeding or failing. If you try it enough times, eventually you will get it. This time, okay, this is actually, I think this is slightly confusing. So they're saying this has been deprecated, but I've actually had problems with it not being there, where when I was depositing Lamports, so I do keep it in here, even though they're saying that function has been deprecated. So we're calling the other function now, and this is the context for it. So what we're providing as an argument is a big number of the gamble amount. Okay, there's an n missing, but yeah, which is defined up above. and the accounts which are defined in a context. So yes, the gamble amount, we use it to run checks to see whether the person has enough money to gamble and to see whether the bank has enough money to pay out double the amount of money. And then we just match every one of these accounts. So the token account, the poolment, the person calling it, which is also the signer, the non-PDA bank account which we've created, and the system program. Although there is no actual, yes, okay. I don't think system program is actually necessary because there's no account being created. Actually, sorry, no, it is. Sorry, it's invoking CPA. Sorry, my bad. Okay, so after this happens, we're checking the balances. So this is the end balance of the bank, and this is the start balance of the bank. So we have the starting point and the ending point. This is a coin flipper. There's only two options possible. So we don't know what's going to happen. That's why we try. So we try either the bank lost and the gambler won the money. So we were expecting the gamble amount times 2 to equal change between the start and then balance of the bank. So either this is going to be true. If this fails, this expect, then this must be true, which is that the bank win and the gambler lost their money. So difference between end balance of the bank and start balance of the bank should be exactly equal to the amount that the person has provided, we've provided in the test, and then we set the flag. And as this runs, then eventually one of these is going to happen. And also we are asserting that the account is not drained. The account we're using actually does have one NFT, so their Lamport balance cannot be 0 at the end. It actually has to be anything but 0. And then yes, at the end of it, we're so we're exiting the loop. So there's no point of looping more if both of the conditions has been fulfilled, which is we've tested that both the win and lose option for either of the parties is possible. As we break from it, then we can continue onwards. This test, we're using the person that has 2 NFTs. Invocation is the same as the one above. So we're using the same amount of money. Lamports, we are providing different token account, and we are providing different the same mint account, and we're providing the public key and signing with the public key of the person from whom the ATA will show that they indeed own 2 different NFTs. And then if this doesn't get rejected, that means it works. Someone with 2 accounts has succeeded. And at the end, we're checking that they did not lose money as well, because they have the right to gamble. Okay, this test, so you can't gamble without NFT. I mean, okay, yeah, you can't gamble. Yeah, that's true. I mean, you can gamble on the contract not working correctly and letting you gamble, but yeah, you can't do it. So we're submitting now as owner with the 0 NFTs. We're providing their account, which is going to have 0 money. Bank and system program exactly the same. We're signing as them. This is just a log for their balance. But this time we're asserting that this color, that their balance of Lamports is set to 0, which should happen if they call, which then did. Well, this time we're going to check that. So the person that couldn't gamble before, this public key, well, they should be able to gamble if we do give them an NFT. So we are actually transferring them NFT from a different account. So let's see the function of the argument list for it. So the connection is said, the payer's anything. It just happens to be mint authority, but I mean, it probably wouldn't be in real life. Source, destination, and the owner of the source account. So we're providing the ATA. So where is it coming from? Where is it going to? And who's the owner that's going to be signing for this? And token program ID. This is more logging. And in the end, we're invoking exactly the same as before. So it is the owner with 0 NFTs. We're signing by them. We actually, where was it? Oh yeah, we had to top them up because they lost money. You see, at this stage they lost money. So if this wasn't done, this whole invocation would have failed. So yes, so we top them up, and this time at the end they don't have a 0 Lamport account balance because they are allowed to do it. Okay, I think this is the final test, which is you can't gamble with an NFT from a different collection. There's a T missing. So yeah, we're starting out just some logging, getting the start balance. We're asserting that, excuse me. So where's this test? Okay. Okay, so this is just logs. Okay, so there's one assertion missing, but that assertion was that I think maybe missed one comment, was that that person has 0 NFTs from the initial collection, but when we get it from their latest collection, they have to have it. So we're basically pulling the associated token account for that person for the new collection and making sure that is more than 0, and they do not have NFTs from a previous one. And likewise, we do exactly the same invocation. So yeah, token account, the new mint, the color, signature of the color, banks unchanged in the system program, and we're logging the balances. And in the end, we're testing that this person as well has been drained. So that was in case to make sure that there was no slip up in terms of just somehow allowing any NFT to allow for this to happen. And this is the end of the test. Maybe not quite as long as the other one. I'm sure there's a lot more sign tests to be added. Wish didn't miss out on the other comment because it had, I think, more helper functions. But yes, it does fill out most of the functionality. We've left some of the fields here, which is the part of your homework, which is we're going to be implementing functionality relating to the counter, functionality related to mint, and to the withdrawal, which doesn't exist yet. That's why there are some fields that are left in here, which has been added to the channel. But yeah, this is the end of this example. I guess now will be time for you to homework or team project. Is that correct?
Yeah, that's the plan. Yes, if people want to go through this or go through the other homeworks and make sure you understand this, or you can also work on on your team projects if you would like to do that. Could we open up the breakout rooms, please? I think it was Danny, wasn't it, from Encode?
Yes. How many rooms are we planning to open?
So I think we usually have 13.
Gotcha. They are open now.
Great. Okay, so yeah, we'll spend the rest of the session. People can work on the homeworks. If you want to go into the breakout rooms, please do so. We'll close the breakout rooms just before the end of the session and come back to the main room then. In the meantime, if you have questions, please pop those onto Slido or into Discord. Thank you. All right, so thank you, everybody. I hope you found that useful. Going through the more complex example and showing you the test there. Thank you, Vincent, for presenting that, and thanks, Carol, for the support there. Tomorrow we will have the usual team day, and just another reminder that Thursday is a holiday in the UK, so there won't be a lesson on Thursday. As always, if you have questions, please put them on Slido or onto Discord and we'll be happy to answer them. Otherwise, have a good evening. Thank you.